Hello. Today's lecture we will talk about section 1.3, rates of change. I'm pretty happy about this book. It has this section that's missing in other books. We sort of assume you know this from other classes, your other math classes, but here it goes into it in a bit of detail. And rate of change is what calculus and precalculus is all about. So if we have a straight line, you probably remember you want to find the slope of this. And to do that, you probably remember it's the change in y over the change in x. Maybe you didn't use deltas, but deltas, if you take physics, you're going to run into deltas a lot. So it's the change in y. Y is up here at this point, down here at that. So the change in y is this over the change in x. And then it'll give you the slope. The slope is, or this change in y, change in x, can also be thought of as the average rate of change. It's average because if this wasn't a straight line, say it was this line, and you wanted to know, well, let's see, I was back here at this value, I was here, and at this value I'm here. What's the average rate of change? It's going to be the change in y and change in x. But that loses a lot of detail. This will give you this line, which is the average rate of change over here. But it's not going to tell you much about this slope here. It actually looks like it decreases in here, and then it becomes very steep. So the average loses a lot of detail. And the slope is often what we're interested in. But calculus is a way of getting from average rate of change to the actual slope. But first, average rate of change, the change in y over the change in x. This means you take y2, say this one was a y2, oops, x2, x1, y1, y2, and this one here is x1, y1. So you go from x1, y1 to x2, y2, and you want to know what was the average rate of change from there. This could be anything. This could be a price of gas your book talks about. I try not to use real world examples like that, because math exists on its own. So you want to know the rate of change of this. If it's a line, that's no problem. No matter where you pick these, you will get the same rate of change. So to get the rate of change, it's just y2 minus y1 over x2 minus x1. And that's what we're going to be doing in this section. We have a bunch of problems like this to find this average rate of change. This sort of foreshadows, that's all there is to average rate of change. Notice average rate of change can be disastrous. Say you went on a trip, and here's your average speed, and you're driving fast here, hit some traffic, pick up speed, and slow down here, and you ended up stopped at both ends. If you measure average rate of change from the beginning to the end, it's both y2 and y1 are 0, so it's 0 minus 0 over, I don't know, some x over 0. So it ends up being 0. So you can lose a lot of detail with the average rate of change, but it's fine for some functions, and we'll use it to get the real rate of change, which is the same as the slope. Okay, let's see. I did want to set up, you'll have some problems which say it goes from like 1 to 1 plus b, which seems like a strange thing to say. I'm going to draw a curve, and we'll try and find the average rate of change using these 2 points. We're going to do it a little differently. We're going to leave symbols in. We're going to say this is x1, and this is x1 plus h. So this point here is going to be x1, f of x1. I shouldn't have put the 1 in. Well, that's fine. And up here is f of x1. Whoops. Whoops. F of x1 plus h. Alright, so our average rate of change is delta y over delta x, which is going to be these two subtracted, f of, what was the h? F of x plus h minus f of x. I've already alluded to this. And this is going to be x plus h minus x. There should be really ones on these. That's fine. So this is the thing that's sort of the fundamental difference equation for calculus. And that's one of the reasons we do rate of change. You can see that the slope here is a good approximation to the slope here, but it's not exactly the same. What we're going to be doing is we're going to make this h smaller and smaller. We'll find the limit as h goes to 0. And as this gets smaller and smaller, this slope estimate gets better and better until it gets to 0, and then it's completely accurate. Then it's the instantaneous rate of change. Which is also the slope. Now if you get a value here, this is going to be increasing here. I'm going to do a different function. And this is sort of the descriptive. Do a function that stops here. You may recognize this as part of a cubic equation. But you can also think of it as your altitude as you're going on a trip up a mountain. So you hike up the mountain. Well, the important thing is it's very intuitive here, so it seems. So you're going very steeply increasing here, but actually you're decreasing here. So that we call these curves. I mean, we say this one is descriptively. We say it's increasing. It has a positive slope, and here it's decreasing. Increasing is positive, and here it's decreasing. This is negative slope. What happens at the very top here? The slope is 0. And as you're decreasing down here, eventually it stops decreasing, and also your slope is 0 too. In precalculus and analysis in general, we're often interested in where these points occur. And this one you may remember is a maximum. Nice reasonable term. And this is a minimum here. Now this is not the lowest point the curve goes. It's lower down here. So these are just where it's locally a maximum minimum. So we say it's a local minimum and a local maximum. These are just terms we're going to use. And here's the highest it gets absolutely. So this is the absolute maximum. And conversely, or also absolute minimum. Terms we're going to be using. So you may see a trick here if we can find out what the slope of this equation is, we can find these local maximum minimums by setting the slope equal to 0. So where the slope equals 0, there's a local maximum or a local minimum. So we 0 is local max or min. That's about it. Okay? Pretty straightforward stuff. We'll have a few problems on this, but we'll all build on it as we get into some more interesting equations later on.